In this video, we're going to go through Gibbs Free Energy. So what is Gibbs Free Energy? Well, it's energy available in a system that can be used to do work. It's used to determine if the system has enough energy to undergo the process for the reaction to take place. Now, we're going to get into the equation here in a second, but I just want to review two terms that you should be familiar with. And the first is enthalpy, which is delta H, and that's energy required or released in a chemical or physical process. So when it's required, that would be an endothermic reaction, it's absorbed, or released, that's an exothermic process. It's releasing the energy. Exothermic processes are favored. That's when delta H is negative. Entropy is energy as a function of temperature that is available for work because it's lost to molecular disorder. Okay, so again, when we talk about disorder, there are lots of different situations. Like if you have a gas, for example, there's going to be a lot more disorder in a gas than there is in a solid because the particles are spread out further. Greater disorder is favored. That's when delta S is positive. Okay, so here's our equation for Gibbs free energy. Delta G equals delta H minus temperature times delta S. Okay, now I want to show you something. When entropy is favorable, that's when you have a positive delta S, and enthalpy is favorable, that's a negative delta S. You're going to have a thermodynamically favorable result because you're subtracting a positive number from a negative. That's going to result in a negative delta G. The other situation, it says when entropy is unfavorable, that's a negative delta S, and enthalpy is favorable, that's a positive. The reaction will never be thermodynamically favorable because this is going to be a negative, this will be a positive, and you're going to end up with a positive delta G, most likely. Okay, so it's not going to be favorable. All right, to calculate the Gibbs free energy for a reaction, compare the Gibbs free energies for the formation of the products with the Gibbs free energies for the formation of the reactants. So essentially what we're going to do is we're going to sum up all of the delta G values for the products. We're going to sum up all of the delta G sum up all of the delta G values for the reactants, and then we're going to subtract them. So this should look awfully familiar. All of these values are located in the appendix of your textbook. So here's an example. It says the decomposition of sodium hydrogen peroxide, H2O2, occurs slowly at room temperature according to the following reaction. It asks us to do two things. It says predict the sign for delta G and then justify your answer. Okay. It tells us that it occurs slowly at room temperature. Okay. So because it's happening at room temperature, we can assume that it's happening spontaneously. Because it's happening spontaneously, we know that delta G is going to be negative. I apologize for my dogs. They are just so excited about chemistry right now. Okay, the second thing it asks us to do is predict the sign for delta S and then justify your answer. Okay, delta S, remember, is our disorder. All right, so we're starting with an aqueous reactant, and then we have a liquid product, and then a gaseous product. So since we're going from a aqueous, or a liquid, to a gas, everything is spreading out further. So because everything's spreading out further, again, if you recall, entropy has to do with disorder. Things that are in the gaseous state are spread out a lot more further, so there is going to be a greater disorder. All right, second example, it says consider the reaction, calculate the value for delta G and determine if the reaction is thermodynamically favorable at 298 Kelvin. All right, so we are going to look up all of these values and basically do what we've been doing. So here we go. Delta G equals, let's go through and let's assign all of these numbers. So HCN is 121, I'm pulling that right from our table over here. O2 is 0. H2O is negative 237.2. CO2 is negative 394.4. And then nitrogen is 0. Okay, so we've got our products. So we have two H2Os, so 2 times negative 237.2. I'm going to add that to my 4 CO2s, negative 394.4, and then 0, N2. I'm not going to even do that one because it's 0. Okay, and then we're going to subtract our reactants. So we had 4 HCN. HCN is 121. Okay, when I do this, be careful with your parentheses. You should end up with the value of negative 2536 kilojoules. And because it is negative, yes, it's less than 0, so it would be thermodynamically favorable. And that's it.